Let's begin by comparing anaerobic and aerobic treatment processes. As you can see in this table, anaerobic treatment operates in the absence of oxygen, while aerobic treatment requires oxygen. This fundamental difference leads to several key distinctions. Anaerobic processes have a much lower sludge production, require significantly less energy, and have a smaller reactor volume compared to their aerobic counterparts. Furthermore, anaerobic treatment produces biogas, a valuable renewable energy source, while aerobic treatment consumes large amounts of energy for aeration. Aerobic treatment, while effective, has several disadvantages. It is an energy-intensive process, primarily due to the need for continuous aeration. It also produces large volumes of sludge, which requires further treatment and disposal, adding to the overall operational cost. Moreover, aerobic systems can be sensitive to fluctuations in organic loading and may not be as effective for treating high-strength industrial wastewater. In contrast, anaerobic treatment offers numerous advantages. It consumes very little energy and, in fact, produces energy in the form of biogas. The low sludge production minimizes disposal costs, and the process is well suited for treating high-strength wastewater with high organic loads. Anaerobic systems are also more compact, requiring less land area. The benefits of anaerobic treatment extend further. The granular sludge developed in high-rate anaerobic reactors has excellent settling properties, allowing for high biomass retention and efficient treatment. The process is also resilient to shock loads and can be operated intermittently without significant loss of performance. Finally, the enclosed nature of anaerobic reactors minimizes odor emissions, making them a more environmentally friendly option. High-rate anaerobic systems are designed to retain a high concentration of biomass, which allows for high loading rates and short hydraulic retention times. This is achieved through various reactor configurations that promote the formation of granular sludge or the attachment of biomass to a carrier material. These systems are capable of treating large volumes of wastewater in a relatively small footprint. The anaerobic filter is one of the earliest high-rate anaerobic systems. It consists of a packed bed of media, such as plastic rings or stones, on which a biofilm of anaerobic microorganisms develops. Wastewater flows upward through the media, and the organic pollutants are converted to biogas. The media provides a large surface area for biomass attachment, preventing it from being washed out of the reactor. The upflow anaerobic sludge blanket, or UASB reactor, is one of the most widely used high-rate anaerobic systems. In a UASB reactor, wastewater is introduced at the bottom and flows upward through a blanket of granular sludge. The gas produced during digestion helps to mix the contents of the reactor and promotes the formation of dense, well-settling granules. To enhance mixing and improve performance, some UASB reactors incorporate an effluent recycle. A portion of the treated effluent is recycled back to the bottom of the reactor, increasing the upflow velocity and ensuring better contact between the wastewater and the granular sludge. This is particularly useful for treating high-strength wastewaters. The expanded granular sludge bed, or EGSB reactor, is a modification of the UASB design that operates at a much higher upflow velocity. This causes the granular sludge bed to expand, creating a fluidized bed that provides excellent mixing and mass transfer. EGSB reactors are capable of achieving very high treatment efficiencies at high loading rates. The heart of high-rate anaerobic systems is the granular sludge. These granules are dense, compact biofilms with high settleability and mechanical strength. From a microbial perspective, they represent a balanced community of syntrophic partners, where different groups of microorganisms work together to break down organic matter. This close association provides protection from toxic shock and results in high methanogenic activity, leading to efficient biogas production. This close-up image reveals the intricate structure of anaerobic sludge granules. They are typically spherical with a layered internal structure. The outer layers consist of acid-forming bacteria, while the inner core is dominated by methanogenic archaea. This spatial arrangement optimizes the centrophic relationships between different microbial groups, enhancing the overall efficiency of the process. These scanning electron microscope images provide a more detailed view of the microbial communities within the granules. On the left, we see a culture grown on acetate as a substrate, dominated by the methanogen methanocida. On the right, a mixed culture grown on sucrose shows a more diverse community of bacteria and archaea. This illustrates how the substrate composition influences the microbial ecology of the granules. This image demonstrates the superior settling properties of granular sludge compared to flocculent and dispersed sludge. The dense, compact nature of the granules allows them to settle rapidly, which is crucial for maintaining a high biomass concentration in the reactor. This high settleability is a key factor in the high performance of UASB and EGSB reactors. The adoption of high-rate anaerobic treatment has grown exponentially over the past few decades. This graph shows the cumulative number of full-scale anaerobic bioreactors for industrial applications. The rapid increase, particularly since the 1990s, is a testament to the effectiveness and economic viability of this technology. This pie chart illustrates the market share of different types of granular sludge reactors. As you can see, UASB and EGSB reactors dominate the market, accounting for a combined 72% of all installations. This highlights the widespread adoption and success of these technologies in various industries. The development of the UASB reactor is largely attributed to Dr. Gatse Lattinga, a Dutch professor who pioneered the concept in the 1970s. His groundbreaking research laid the foundation for the development of high-rate anaerobic treatment and has had a profound impact on the field of environmental engineering. This table provides a comparison of the design loads for full-scale UASB and EGSB reactors. EGSB reactors can handle a significantly higher average design load of 20 kilograms COD per cubic meter per day, compared to UASB reactors at 10 kilograms COD per cubic meter per day. Both systems achieve a high removal efficiency of biodegradable COD, typically between 85% and 90%. High-rate anaerobic treatment has found widespread application in various industries. The most important markets include breweries and the beverage industry, distilleries and the fermentation industry, the food industry, and the pulp and paper industry. These four wastewater types account for a remarkable 87% of the market. This image shows an anaerobic lagoon used for treating wastewater from a food and beverage processing plant in Washington. Anaerobic lagoons are a simple and cost-effective form of anaerobic treatment, but they typically require a large land area and have lower treatment efficiencies compared to high-rate systems. The contact process is another type of anaerobic treatment system where biomass is maintained in suspension. The wastewater is brought into contact with a high concentration of anaerobic microorganisms in a continuously stirred tank reactor. After digestion, the biomass is separated from the treated effluent in a settler and recycled back to the reactor. This image shows a contact process digester at a food processing plant in Virginia. Here is an example of a UASB reactor installation in the Netherlands. The compact design of the UASB system is evident in this image. The two large tanks are the UASB reactors, where the anaerobic digestion takes place. The smaller building in the center likely houses the control systems and other ancillary equipment. This image shows a UASB reactor with internal circulation at a brewery in Switzerland. The tall, slender design of the reactor, which is 20 meters high, is characteristic of systems with internal circulation. The internal circulation is driven by the biogas produced during digestion, which creates a natural mixing pattern within the reactor. This is another example of a UASB reactor with internal circulation, this time at a kraft paper mill in Alabama. The treatment of pulp and paper mill effluents is a challenging application due to the presence of complex organic compounds and potential inhibitors. The robustness of the UASB process makes it a suitable technology for this industry. This image shows an EGSB reactor at a yeast and pharmaceutical plant in the Netherlands. The tall, slender design is also characteristic of EGSB reactors, which operate at high upflow velocities to fluidize the granular sludge bed. This results in excellent mixing and high treatment efficiencies.